Hello everyone, thank you for watching this video. My name is Meyer and today I will talk about graph convolutional networks for 3D object detection on radar data. In many radar processing pipelines, the radar data can be represented at some point as a range beam Doppler tensor, where each beam corresponds to some specific azimuth angle and the Doppler dimension encodes the relative radial velocity. So the radar data is in polar coordinates, and in many object detection networks there is some transformation of this data into Cartesian space through bilinear interpolation. However, depending on the resolution of the grid after the interpolation, information might be lost, especially in the near range. The goal of this work is to use graph neural networks on radar data for object detection and to test the following two hypotheses. Using information of the Cartesian distances between points of data in the radar signal can be used in graph neural networks to improve the performance of object detection tasks on radar data. And isotropic graph convolutional networks are beneficial for radar data because the radar signal often is not located in just one pixel, but it usually fades into neighboring cells. There are many ways to define convolution layers on graphs. In this work, the graph convolutional operator of Kipf and Welling is used. The c-dimensional node features of n nodes in the graph can be summarized in a feature matrix X, which is propagated through a GCN layer with a layer-specific trainable weight matrix theta. You can see the propagation rule here. A hat is the adjacency matrix A, which contains the edge weights with inserted self-connections, and D hat is its diagonal degree matrix. The first part of this equation corresponds to a weighted sum of feature vectors, where the weighting is done through the edge weights. The weighted sum matrix is then multiplied with the trainable weight matrix theta, which for each output feature channel contains exactly one weight for each input feature channel. This isotropic property is a substantial difference compared to a standard 2D convolution. Here you can see the architecture of the network. The radar tensor is converted into a graph, where each node corresponds to a pixel in the range beam map, and the node feature dimension corresponds to the Doppler dimension. The graph is then passed through a graph neural network, and afterwards a pyramid ResNet outputs 3D bounding boxes for predicted objects. Three versions of this network are trained and evaluated. As a baseline, the graph convolutions are replaced by standard 2D convolutions, and two trainings are performed with graph convolutions. Once it is trained with identical weights for all edges in the graph, and once the edge weights are calculated from the Cartesian distances between each two nodes. We use the average precision to evaluate the object detection performance of the network. Inspired by the Kitty dataset, we evaluate three difficulty levels, and because radar is not as geometrically accurate as LiDAR, we use a relatively small IU threshold of 0.3. Here you can see the precision recoil curves for 2D bird's eye view evaluation and the same curve for 3D evaluation for the predictions of our network with graph convolutions. The network without graph convolutions performed roughly 10% worse for all 3 difficulty levels. Surprisingly, adding the Cartesian distance information as edge weights did not improve the performance. Maybe because of the way how the radar data is created, it is necessary to distinguish between Cartesian distance in range direction and Cartesian distance in beam direction. Previous publications about object detection on radar data were either using a very simple highway dataset or only evaluating their performance up to a maximum range of 20 meters. Therefore, it is impossible to directly compare our object detection performance with theirs. Nevertheless, taking into account different radar sensors, different street scenarios, different maximum ranges, and different IOU thresholds, our results are in a similar order of magnitude as a previous state-of-the-art. Using graph convolutions for information aggregation and extraction of features from the radar tensor, we improved the object detection performance by plus 10 percentage points and achieved state-of-the-art performance. This demonstrated that due to their properties, graph neural networks are very well suited for radar data. However, calculating the edge weight from Cartesian distances between nodes did not change the performance of the network remarkably. The reason for this might be that the signal is more distributed in the beam dimension than in the range dimension, and these dimensions need to be handled separately. In future work, we will investigate if the performance can be improved by using graph convolutions with separate attributes in range and in beam direction. Thank you, and I hope you enjoyed the video.